A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, Project Administrator, iLEAPS, welcomes you all on the occasion of our last talk of this year, that is 12th talk of 2022 in iLEAPS Global Colloquium series. So iLEAPS is Integrated Land and Atmosphere Interactions, which is a global research project of Future Earth. iLEAPS provides understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. So the prime purpose of this colloquium is to introduce the scientific society of the people with the distinguished and significant work of eminent scientists from all over the world. It is a very bright opportunity, particularly for the early career researchers, to interact with them and establish the bridge between the ideas and knowledge through this platform. So the speaker of our today's event is Dr. Vaishali Naik, who is research scientist at NOAA Geophysical Fluid Dynamics Laboratory. Her research interests are in atmospheric chemistry and composition, climate change, air pollution, biosphere-atmosphere interactions. So she applies global Earth system models in conjunction with observations to study the interactions and feedbacks between atmospheric chemistry and composition and human-induced climate change. She has contributed to the 5th and 6th assessment reports of the Working Group 1 of the IPCC. Vaishali also serves on the advisory board of NECAR's Community Earth System Model. Vaishali earned a bachelor's in chemistry from Delhi University, India, and received her PhD and MS in atmospheric sciences from the University of Illinois at Urbana-Champaign. So today she will be talking about the role of short-lived climate forcers in the climate systems and key findings from the IPCC AR6. So this is the chapter which assesses about the evolution of the reactive chemicals with lifetimes of about 2 decades and their effects on climate and air quality. So she will discuss about the projections of air quality and climate in response to spatially varying projections of short-lived climate forcers emissions with opposing climate effects. So now I will again welcome Dr. Vaishali Naik to put some light on this topic. Dr. Vaishali, the floor is all yours.
Thanks, Pallavi, and you will give me sharing permissions?
Yes.
Okay, so let's see if this works. Okay. Can you see my screen?
Yes.
Okay. Let's do this. Can you see my screen?
Yes, in full mode. It's
Great.
I can see.
Great. Thank you so much. Thank you so much, Samina and Pallavi, for the invitation to speak at the iLEAPS Global Colloquium series. So as Pallavi mentioned, I will be summarizing the findings from Chapter 6 of the IPCC AR6 Working Group 1 report on short-lived climate forces. The IPCC report, the Working Group 1 report came out in August of 2021. And the nicely formatted chapter showed up sometime early summer this year. If you haven't had a chance to open the chapter, then this talk will hopefully get you motivated to open the chapter. And if you've had a chance to look through the chapter and have questions and clarifications, then hopefully I can provide those at the talk today. All right, so before moving on, I would like to acknowledge my co-authors, my co-CLA, Sophie Zopa, and my lead authors on the chapter, as well as my the almost about 50 contributing authors who provided important input to the chapter. So just to give you a quick look of the AR6 Working Group 1 report's outline and see where this chapter sits. So basically, as you know, that the AR's IPCC reports are comprehensive, especially on Working Group 1, comprehensive reports of the state of knowledge on the physical climate science. And this report is then divided into 3 parts with large-scale climate change, climate processes, and regional climate information. And the short-lived climate forces chapter sits right in the middle within the climate processes. However, short-lived, although all the points of short-lived climate forces are considered in the chapter, but the SLCFs are referenced in different chapters here, pretty much throughout the report. So just to give you like an overview of the chapter itself, as the chapter discusses the evolution of reactive compounds and their effects on climate and global air quality. The chapter is divided into 8 sections, and the first section, of course, talks about the importance of SLCFs, defines SLCFs, and provides a background on how SLCFs have been considered in past IPCC reports. The next 3 sections talk about the historical evolution of emissions and abundances and the climate effects of SLCFs. Additionally, the section on changing climate on air quality. And then finally, the last 2 sections talk about the future projections of air quality and climate response to various projections of SLCF emissions. And you will see in the chapter there are a number of figures and boxes as well that can potentially be used for your teaching and can be referenced further. So to get into, so my talk will basically go through pretty much the different sections of the chapter. May not be in the same order, but overall you'll get a taste of all the material covered in the different sections. So first, what are SLCFs? SLCFs are a set of chemically and physically reactive compounds with atmospheric lifetimes typically shorter than about 2 decades, which means that SLCF abundances are highly heterogeneous spatially, although there are some SLCFs that are well mixed because of their slightly longer lifetime, but still shorter than 2 decades, which would include methane and some of the HFCs. And here, because of the short lifetime and the highly heterogeneous spatial distribution can be clearly seen for tropospheric nitrogen oxide, as shown here in one of the figures from the chapter. They can be emitted directly, when they will be termed as primary. So methane is a primary SLCF, or they can be formed in the atmosphere, which means that they are secondary. Which means that they're secondary, and so ozone or sulfate aerosols would be secondary pollutants or secondary SLCFs. They can influence the Earth's radiation budget directly or indirectly uh, through their interactions with radiation or with other components of the climate system. So just to elaborate further, how do SLCFs influence the climate system? First, many SLCFs are also air pollutants with detrimental effects on human health and ecosystems. They are emitted from some of the same sources as other greenhouse gases, as you see in the bottom panel of the figure here. And as I mentioned, SLCFs can influence climate interacting directly with radiation, either absorbing, scattering, or through albedo changes, or by perturbing other components of the climate system, for example, interaction of aerosols with clouds. The net effect of SLCFs on temperature is either a warming or a cooling, and that is the unique aspect of SLCFs, because they are, in that sense, they are different from the greenhouse gas climate effects because of their cooling effects. Additionally, climate-induced changes in SLCFs can lead to Earth system feedbacks that can either amplify or diminish the initial climate perturbation. And by amplification would mean a positive feedback, or diminishing would mean a negative feedback. So how have SLCFs evolved over the past few decades? So based on the different emission inventories, we assess that over the last decade, there have been strong shifts in the geographical distribution of emissions, particularly anthropogenic emissions. And additionally, for this audience, we also assessed how emissions from natural processes are changing. So basically, emissions from natural processes are increasingly being influenced by human activities, either via climate change, land use, land cover changes, or atmospheric CO2. We assessed that the understanding of emission processes in the natural system has improved, but there are uncertainties that make it difficult to predict how shifts in climate and different relevant environmental factors will influence these natural system emissions. So in response to the varying geographical distribution of emissions, what has happened is that there have been changes in atmospheric abundances of SLCF, especially the ones that are highly variable, with strong regional variation in trends of ozone and aerosols and their precursors. So there are these two figures that I'm showing you from the chapter. On the left, you have the tropospheric NO2 column, and it clearly shows from the satellite, it clearly shows that the trends in NO2 have varied regionally over North America and Europe. They were increasing up until about 2010 period, and have now started declining. And similarly, for South Asia, there has been a continued increase, and for East Asia, the NO2 has started declining. And for tropospheric ozone global burdens, we see that the tropospheric global ozone burden is showing a continued increase in the recent decades as well. So additionally, we assessed the impact of COVID-19, the restrictions that were put in on emissions, and their impacts or implications for air quality and climate. Note that the studies that were assessed for this box were only up until January of 2021. And so our understanding was based on that, and what we saw was that the emission reductions in 2020 associated with the measures to reduce the spread of COVID-19 did lead to a temporary but detectable effects on air pollution. For CO2, despite about a 7% decline in emissions, the atmospheric CO2 concentrations continued to increase in 2020 with no detectable decrease in the growth rate. And because of the reduction in aerosols, we did see a small but temporary increase in total radiative forcing, which was undetectable above natural variability. So in response to changing emissions of various various LCFs, this has implications for oxidizing capacity of the atmosphere, the hydroxyl radical. And here, this change is expressed in percent anomaly relative to the mean over 1998 over 2007. The top figure shows the pre-industrial to present, and the bottom figure is a zoom in of the time period for which there is observational constraints that have been derived, so 1980 to present. And what we found from various assessment of the various studies, that there is no significant trend in global mean tropospheric OH concentration from 1850 up to about 1980. And then from 1980 to the present, OH has remained stable or exhibited a positive trend, and there is medium confidence on that. And the positive trend has been attributed to increasing NOx emissions that are driving the increases in OH. So, so the next question then to address is how have changes in SLCFs affected climate? And before I describe the answer to you, I'd like to introduce two terminologies. First, effective radiative forcing, which is a measure of the change in the Earth's top of the atmosphere radiation budget in response to any perturbation, and specifically this takes into account the atmospheric and chemical adjustments. And what I mean by that over here is that once you perturb the baseline atmosphere, in response to that perturbation, either an increase in greenhouse gases or aerosols, there is an instantaneous change in the radiative balance, which then leads to adjustments in either the chemical composition or adjustments in clouds and water vapor and temperature. All of this without taking into account any change in surface temperature. And this adjustment aspect is included in the effective radiative forcing, unlike the radiative forcing concept, which did not take into account the various other adjustments besides the stratospheric temperature adjustment. And in addition, I would like to introduce emissions-based ERF and concentration-based ERF for SLCFs. So what emissions-based ERF do is that first they were introduced in AR4 to attribute the climate response of all species to emissions of a single compound, providing a metric or a means of quantifying the effect of mitigating emissions of a pollutant. And as an example, we see for a change in methane emissions, it'll influence methane lifetime, ozone, stratospheric water vapor, aerosols, and lifetimes of various HFCs. So the emissions-based ERF for methane will quantify each of these responses. Whereas for a concentration-based methane ERF, basically it represents the net effect of methane emissions and changes in lifetime, which are then of course affected simultaneously by changes in NOx and CO and VOC. So we relied on comprehensive Earth system models that represent the coupling between various interactive atmospheric chemistry and aerosols to quantify the emissions-based ERF. The concentration-based ERF, you've seen the bar plots, they were assessed in chapter 7, whereas in this chapter, we quantified the emissions-based ERFs. So over the 1750 to 2019 period, changes in SLCF emissions, especially of methane, NOx, and SO2, have had substantial effects on the ERFs. It is difficult to directly compare the ERF estimates with those that were assessed in AR5. However, there are some notable updates that one can see. Forcing due to methane and NOx emissions are stronger than in AR5. SO2 emissions dominates the aerosol forcing via aerosol cloud interactions, and this is also the largest uncertainty or source of uncertainty in the total rated anthropogenic forcing. Black carbon forcing has been significantly revised downward since AR5 for and then these estimates of ERF provided a strong foundation for the assessment or the quantification of global surface air temperature responses to individual SLCF emissions. And you can see the sign of the year or the magnitude, the contribution of each of these species to GSAT follows their contributions to ERFs. In the study, of course, we relied on comprehensive Earth system models for ERF calculation, but we could not do that for GSAT, given the computational expenditure that would be required to run for each of these species. So we relied on a simple impulse response function to obtain these contributions. And from there on, this provided then the basis for this figure that you've seen in the SPM now, which clearly showed that the observed warming is driven by emissions from different human activities, and the aerosols have partly masked the warming from greenhouse gas emissions. So in addition to impacts on surface air temperature, aerosols also affect precipitation. And their impacts on precipitation was assessed in chapter 8 in much more detail. I'll not go in the specifics, but the overall effect of anthropogenic aerosols is to reduce global precipitation and alter large-scale atmospheric circulation patterns. And there's high confidence in this estimate. In more recent work, this role of aerosol on precipitation and especially a hydrological cycle there has been a renewed interest in quantifying this aspect and also just highlighting the role of aerosols in climate risk from their influence on precipitation. All right, so moving on. So how will climate-induced changes in SLCFs feedback on climate? So what I mean here is that the climate-induced changes in Earth system processes that are mediated by SLCFs, natural emissions, or atmospheric chemistry acting on timescales of years to decades. And these changes can either diminish or amplify initial climate perturbation. So you have a change in climate that would then affect emissions of, say, dust, all of these individual species, and then they'll respond in terms of either directly affecting the radiation budget further or through atmospheric chemistry changing the methane lifetime and changes in ozone. So the way this is quantified, these feedbacks are quantified, are in terms of the feedback factor, which is a measure of change in net energy flux at the top of the atmosphere for a given change in surface temperature. And the feedback factor is quantified entirely from ESMs, the Earth system models, that couple the physical climate with atmospheric chemistry to land and ocean biogeochemistry. So in this assessment, and so this feedback factor is used for the quantification of equilibrium climate sensitivity, as shown here in this equation. And unlike in previous reports, which only included the physical feedback for the quantification of ECS, in this assessment, ECS also includes the Earth system, the feedbacks from the Earth system processes. And therefore, this the assessment of feedback parameter becomes important as to how this feedback parameter influences the ECS. So one thing to note is that we did not assess the feedback factor for wildfire emissions, mostly because we will need to rely on models that include interactive representation of wildfires, which is progressing, but hasn't yet progressed to a point where we can quantify this in a more robust way. So what do we find for feedback? So SLCF-mediated feedbacks, climate feedbacks, what we find is that they diminish the base climate response, which means that they lead to cooling or cooling. So what this plot shows over here is a feedback factor from for these different individual components, including the wetland methane as well. And when you look at the total sum, it's negative, but there is a large uncertainty. So this uncertainty in the sign and the magnitude of feedback parameter basically comes from the diversity in representation of emissions, chemistry, and aerosol processes across the different Earth system models. And it also represents our process, an uncertainty in our process understanding, the representation of these various natural emissions varies and depends on how far our understanding has evolved, and that is kind of represented here in this figure. So when you sum it all up and when you compare these SLCF feedbacks, combining them with also geophysical feedbacks as well, biogeophysical feedbacks, you get a value for the feedback parameter that is very close to 0. So what this means is that these feedbacks don't necessarily contribute to the magnitude of the effective climate sensitivity, but they contribute to the uncertainty in the ECS. And we conjecture that ESMs that are likely to have a lower climate sensitivity than their physical climate counterparts because of the inclusion of these additional biogeochemical, non-CO2 biogeochemical feedbacks. I should also mention that the biogeophysical and the different physical feedbacks and the CO2 feedbacks were quantified in different chapters, chapter 5 and chapter 7. We kind of brought it all together in the summary from the figure in the technical summary. Okay, so moving on. So the two additional questions that I wanted to highlight here is that how will air quality and climate respond to future changes in SLCFs? And what are the implications of climate change on air quality? So for this, we relied on the shared socioeconomic pathway scenarios to make these projections. The SSPs were developed by the Integrated Assessment Modeling Consortium, developed in support of the IPCC 6th assessment report. In the working group 1, we used 5 SSP scenarios, and these are all based on 5 narratives that describe the broad socioeconomic trends that could shape the future society. And these are, again, illustrative emission scenarios. So emissions vary between SSPs depending on the socioeconomic assumptions, levels of climate change mitigation. So for example, for CO2, you see clearly the SSP 585 that has no climate change mitigation. The CO2 emissions double by almost by 2050, and similarly for SSP 370, where the CO2 emissions double by 2100. But for aerosols and non-methane ozone precursors, these emissions also included air pollution control, levels of air pollution controls, and therefore the trajectories of SLCFs or air pollutants then differ from the greenhouse gas emission trajectories. And you can clearly see that for a scenario where CO2 emissions are increasing drastically by 2100, for example, SSP L585, you have a sharp decline in, for example, for SO2 emissions and NOx emissions. And so, additionally, these SSPs were different from the representative concentration pathways that were used in AIR5. The RCPs used a similar assumption of air pollution controls across the different scenarios, which then resulted in not a very wide range in the trajectories for different pollutants, BC, sulfur, sulfur dioxide, NOx, and VOCs. So the SSPs covered or provided a better coverage of the diversity of future options in air pollution management, and therefore span a wider range of the SLCF emissions. So that allows us to better capture the various trajectories that might happen in the future, at least using these 5 SSPs. So then we used results from the scenario MIP and the AirChem MIP activities. These are the multi-model intercomparison projects that various Earth system and climate models participated in to predict or to project various climate change indicators, as well as for air pollution, in this case, ozone and PM 2.5. And what I'm showing you here are 2 figures from the chapter that show the trajectory of or the future changes in surface air pollution for ozone and PM 2.5 from 2015 to 2100 for different aggregated regions. And of course, this posted plot is too difficult to gauge exactly the main, the key points that come out of this. But what the 3 points that do come out of this is that there is strong regional heterogeneity in future air pollution projections. And that highlights the scenario uncertainty in the different parts of the world. And there is large model diversity across global model projections, and that highlights the different the uncertainty in the model structure, like the different aspects that are included in these different models. And then additionally, what we see is that the future air pollution will be driven by both air pollution and climate change mitigation policies. And that becomes clearer here in this plot, which basically shows percent change in PM 2.5 and ozone, PM 2.5 in purple and ozone in green. And you have better air quality going towards your left and worse air quality going towards your right. So what we see, and for the different SSPs that are also labeled in terms of their level of climate change mitigation and level of air pollution. So in the near term, in 2040, what we see is that there are small improvements of worsening air quality in a world that is dependent on fossil fuels, despite strong air quality controls. And we also see that there is best improvements in air quality in a decarbonized world, combined with strong air pollution controls. So SSP 1261, SSP 119, that also include strong climate change mitigation and high levels of air pollution control. And this persists over in the longer term by 2100. So in summary, what we say here is that the future air pollution will be driven by both air pollution and climate change mitigation policies. So then additionally, as I mentioned earlier, we also looked at the projections of global surface air temperature in response to the changes in SLCFs following the different SSP scenarios. And so here we wanted to assess not just the net effect of the SLCFs on GSAT, but to better understand where the net effect comes from. We also had to assess the responses to individual or at least grouped SLCFs. So in this case, aerosols, methane, ozone, and HFCs. And we obviously could not rely on global Earth system model for doing this individual assessment, given the computational resources that would be required to run these simulations. So we based or this contribution from SLCF to changes in GSAT was then calculated based on the global mean ERF from various components, and then combining all of that into using a two-layer emulator for the climate response. And so if you look at the response individually, the declining methane, ozone, and HFCs in these scenarios lead to cooling, whereas declining aerosols leads to a warming. And then this has implications for the net effect, which is then all summed up over here. And what we see is that there is warming from SLCF changes, which is quite similar across the SSPs in the near term, but there's more diversity in the longer term. And so this can be better summarized here. And what we see is that the future changes in SLCFs will cause additional warming relative to 2019. Here again, this is a bar chart of the GSAT changes in response to the individual aerosols, methane, ozone, and HFCs in the different colors, and the net SLCFs plus HFCs in the diamond sign. So in the near term, as I mentioned before, in the near term, this warming is driven by the warming effect of increasing methane ozone from no climate change mitigation and limited or no pollution control. And it is also driven by decreasing aerosols from stringent climate change and pollution mitigation, which we see in the SSP 126 and 119 scenarios. And as I mentioned before, that there is much greater diversity in the responses, but this in the longer term, this net warming is lower in scenarios leading to lower global air pollution, as well as methane emissions are also mitigated. And so we wanted to look a little bit deeper into the role of methane, and therefore we relied on two additional scenarios, simulations that were done by AirChem MIP and also based on the emulators. So this was based off of SSP 370, which had no climate change mitigation and lower air pollution controls. And we took a sensitivity or assessed a sensitivity simulation, which included high methane and low SLCF, so high air pollution control. And then SSP additional one where we included both low SLCF and low methane. So high air pollution controls plus additional methane mitigation. And what we see is that in the scenario with low SLCF and high methane, you have, of course, decline in aerosols and non-methane ozone precursors, which then leads to additional warming coming from the aerosol, coming also from methane. But there is an improvement in PM 2.5 air quality. But if you also include declines in methane, then methane offsets the warming from reduced aerosols and non-methane ozone precursors. Additionally, it also improves air quality. So then this provides, reducing methane, strong, rapid, and sustained methane mitigation will limit warming and also lower air pollution. So right after the report came out, there was a feeling in the media that we are focusing too much on methane. But what we did say in the report is that, of course, strong, rapid, and sustained methane mitigation is required, but only sustained CO2 emission reductions will allow long-term climate stabilization. So this was a key point that we made in the chapter, as well as in the technical summary that went up as well. So then, coming to the final question that I wanted to address here is, what is climate? How is air quality going to evolve in response to only climate change? And so what we found in our assessment is that climate change is expected to have mixed effects on future air quality. For ozone, increases in or a warming world will basically decrease ozone pollution in regions, in remote regions, in response to increasing water vapor, and over polluted regions, ozone will increase, and that was nicely showed here in the plot where we looked at the surface ozone change at different warming levels based on the SSB 370. And as temperatures increase, you have polluted regions. Basically, ozone increases in the polluted regions as temperature increases, and it's clearly shown here in the plot. For PM 2.5, there are mixed effects. PM 2.5 can increase or decrease in response to the climate change. However, stronger effects are not excluded locally in regions prone to specific meteorological conditions that lead to the buildup of PM 2.5. However, in all of this, our confidence was low due to the uncertainty in the response of the different processes in the natural systems. For example, for ozone, stratospheric and tropospheric exchange becomes important. Natural precursor emissions, how they will change or respond to climate change, including BVOCs, wildfires, and the different, and lightning knocks and the different marine aerosols. So with that, I wanted to highlight or end with some questions that come out of the chapter after you've read through in terms of what next. Where are the future research opportunities? And so what we felt is that there is a need for an improved assessment of future air quality and climate effects in response to SLCF emission changes. And especially in terms of the climate impacts, the aerosol indirect effects are the most uncertain, as you saw. And so how climate will respond in the near term in response to changes in aerosol emissions that are being driven by air quality policies that are being put in place in different parts of, especially parts of the world where they haven't been controlled. How the climate will respond in the global sense, I think that's where a push is needed further. And again, this is what I've shown you is that mostly the studies have focused on global surface temperature, but additionally, precipitation becomes important. And as I say, the regional climate change and not just surface temperature responses, but precipitation responses also become important to explore. And further, I think we need a improved assessment of climate change effects on air quality, particularly looking at compound effects, coupled effects of extreme air pollution coupled with extreme weather events. That I think those studies I think are needed that kind of provide a more combined effect of both air pollution and weather extremes. Additionally, climate model biases translate to pollution biases in global models. So this is more from a modeling perspective. Uh, uh, the models that are either too hot or too cold then exaggerate these effects, these impacts. So we need to reduce these climate model biases, which can then provide us better estimates of pollution events as well. And finally, in terms of the SLCF feedbacks, I think improved process understanding is needed, and especially in a community with iLEAPS, there's work going on understanding the different interactions with the land surface and atmosphere. I think this is where a push is needed for process understanding of the different natural systems. And further, a comprehensive evaluation of ESMs is needed to better to disentangle these complex interactions as these ESMs represent new information about natural and anthropogenic processes. It of course increases their realism and enhances their accuracy, but it is also not clear how this incremental enhancement in the complexity influences these our model results and our understanding of the SLCF climate feedbacks. So I think this is where again, like research opportunity is available to kind of push and come up with a sophisticated analysis as well as sophisticated simulations to better nail down these SLCF climate feedbacks. And so with that, I will end. Thank you so much.
Thank you so much, Vaishali. It was really great listening to all your adventure, actually, about exploring these different SSP scenarios and coming up with its results and the projections, how the world will look in 100 years time. And it's a bit scary also. So I'm looking at the questions. Unfortunately, I don't see any questions. So in the meantime, maybe I can ask, because I have a question, because we are always talking about this atmospheric chemistry model developments and how to improve the processes and all. And we all know that the biases in models can result into erroneous representation of the projections or whatever. So where do you see these atmospheric chemistry models in 5 years time from now, or 10 years time, to solve all these problems?
So what I do see is that we will continue to enhance the complexity of the Earth system models. We want to, put in more realism in these models. And with that realism, of course, we also want to explore the different processes. Observations are our best tools to compare and evaluate these models. So, and given that the observational community and the observations are now providing us a longer term look in terms of, we have now longer term data that we can then use to look at the models and evaluate and analyze model results in more sophisticated ways that will then help us improve the representations. So I do feel like this is not just one single community problem. It's observational, fundamental science, and the modeling, three-legged tool, basically, this tool that needs to interact and get together to make advances in our understanding of atmospheric chemistry and climate interactions.
Okay, thank you. Yes, thank you very much. Do you see any questions, Pallavi? I'm just looking at the question and I don't see anything. Pallavi, are you muted?
Yes, there is one question from Saurabh Sonwani. Many thanks for this great talk. I have few questions. Question number one is, some studies mentioned about brown carbon that is responsible for the atmospheric warming. May we consider BRC as climate warming with other short-lived pollutants? That is question number one. And the question number two is, if we consider regional climate, then what are the variable or climate factors we must consider?
So thank you for the question. Brown carbon is something that we did want to address in our chapter, and I think we do in section 6.3. The problem we did find is that there are not very many studies, and whatever there are, they vary, and especially from a global perspective, we were not able to, again, like the models do not include a very good representation of brown carbon at the moment, and not many models do consider brown carbon. So hopefully in the next 5-6 years, there will be progress in the representation of brown carbon in the models, as well as better understanding of their effects on climate from a fundamental experimental observational sites as well, and that would then allow us to consider the effect of brown carbons on climate and air quality. In response to your second question, in terms of regional climate, most importantly, I feel the hydrological cycle, precipitation, and temperature. They're both. How will they change in response to both local aerosols and global aerosols? I think that becomes an important question to address. People, and then one can even further analyze different simulations to look at various impacts in terms of the climate risks, in terms of, as emissions increase, of course, aerosol increases, how will they change precipitation, things like this. So that's where one would push towards.
I hope, Saurabh, you got your answer. Okay, thanks, Vaishali. The next question is from Gary Heyman, who is our iLEAPS IPO. He is asking that, can you expand on the OH trend and what it implies for the understanding of the global methane cycle, methane sources and sinks?
Right. So OH, basically, in the chapter, we relied on both observationally derived, because OH is not measured directly. We rely on methyl chloroform as a proxy to derive OH concentrations and trends. We relied on both observationally derived estimates and global models, and clearly there was there was a conflict between observationally derived trends in OH, which was the observationally derived trends basically were pretty flat. There were no trends in the observationally derived constraints in OH, whereas the global models showed an increase from 1980 to present. So we then, you know, we kind of assessed it in such a way that we said, okay, there is either a stable trend or it is increasing. And so from the models, what additional work that was done by David Stevenson, looking at the air commit models, the models showed that when you have increasing NOx and increasing SLCFs, basically driven by NOx, was driving this increase in the OH. Now, the implications might be that as we go forward in time, you know, as NOx emissions, you know, if they continue to increase the way they are increasing, you have increases in OH, and that would then reduce methane lifetime. But if, as air pollution controls come into play and NOx emissions decline, then you have a decline in OH, and then that would increase the methane lifetime. And this is something that just recently came out in a paper by the Philip CIS group, where they looked at the impact, where they looked at the growth in methane or the decline in growth in methane in 2020 versus 2021. So increase in methane, and they attributed that increase in methane to two reasons: one, increasing wetland methane emissions, and two, a decline in OH led by a decline in NOx, which happened because of the COVID restrictions. So clearly there are great implications for changes in pollutant emissions for OH, and therefore on methane trends as well. I hope that answers your question.
Thank you very much, Vaishali. Samina, is there any more question? Because I am not able to see any more question now.
No, I don't see anything. Just a comment from Gary saying that it's an excellent talk.
Yeah, it's a nice talk.
That's really nice. So if there is no more questions, we can just conclude the session, Pallavi.
Yeah,